Deep learning approaches for automated seizure detection from scalp EEGs. I'm Jonathan Petto. I'm working with Shifra Abitan and Guy Bar Yosef, and we worked with the data set we got from Temple University.
The primary way that physicians are able to diagnose brain-related illnesses like epilepsy and seizures is using EEGs. And right now, a doctor has to sit over a computer for many, many hours in order to pick the seizure out of the EEG. So there's a real need to automate this process. However, before Temple released their corpus, there was not enough data in order to apply deep learning. But now that they've released their corpus, it's possible to do so. There are a few models on the market, but all of those models suffer from having too high of a false positive rate. And so therefore, no doctor will ever use them.
So our data set by the numbers. So the data set is composed of 642 subjects. That's a total of 1,423 sessions, which make up 922 hours of data. Out of 1,423 sessions, only 447 of them contain, at least in some part of them, contain seizures. And that translates to 63 hours of seizures, or 6.8% of the total data.
So while working on this project, there was a competition announced by two different organizations that came together in order to try to push the research in this area forward. And I think this underscores and highlights how important this particular issue is. So the goal of the competition was to build a model that can detect seizures and detect the least number of false positives and use the least number of channels as well. And you can see this reflected in the scoring metric, which is displayed on the bottom.
So our contributions for this project are as follows, and we'll go into details for all of these later on. We developed a robust pipeline, which we used to train, evaluate, and validate our model. In this pipeline, we have pre-processing and post-processing scripts. The data pre-processing scripts that we used are relatively minimal compared to Temple University's state-of-the-art model. We'll talk about this more later, but we tried, one of our goals going in was to show that we could use less pre-processing and delegate the pre-processing that Temple did, for example, to our deep learning model. Speaking of our deep learning model, we developed a novel architecture that Johnny will talk about in a second, but this model, as far as we know, has never been used before for seizure detection. As part of our post-processing scripts, we did different types of filtering. We went through a voting mechanism. We tried moving averages. We tried the Savitsky-Golay filter. And we used a combination of these as at the end. And that's that.
Yeah, so as Guy talked about, their model consisted of a pre and post-processing stage that were not deep learning, right? So the pre-processing stage consisted of multi-rate filter banks, and then the post-processing stage consisted of linear regression or polynomial regression, whatever it was, and a bunch of other things, right? But in the middle, what they had was a CNN and LSTM, the idea being taking context, right? So you have a window of the EEG, and the LSTM allows you to take into consideration some history of what happened before. And then also the CNN allows you to look at a region. It gives you some spatial awareness, which is important for a signal, right? For being able to detect the seizure. So we built a transformer-based model, which we call TABS, or transformer-based seizure detector. And we're going to go a little bit into what the transformer actually is. Transformer is a neural network architecture that is based on attention, specifically self-attention and specifically multi-head self-attention. It takes a multi-head self-attention and has two fully connected layers afterwards. So what exactly is attention? Attention is a function that takes in three matrices, Q, K, and V, which are query, key, and value matrix, and basically scales the value matrix by like the correlation or the inner product, or however you want to look at it, of the query and the key matrix, right? So there's the inner product, and there's a softmax over that, right? With when you see that's divided by the dimension, and basically what you could think of what that's doing is that it's looking at the value matrix and giving scale of what is more important in the value matrix. So you see here we have some context, we have some history that we're taking into consideration. Now, self-attention, Q, K, and V are all the same matrix. Now, multi-head attention is attention with projections, right? So you see we have these W matrices. Basically what this allows us to do is that the model can learn a projection of the query key and value matrix and then perform the attention over it. Now let's take a look at our model architecture. So you see here we have our figure. The first thing we did was we had a 1D convolution. Now this 1D convolution goes from the 19 channels that we're using, the 19 uniform channels, or 20, depending on which model, or the channels which are the EEG electrodes on the brain, into 50, and it's a kernel size of 5. And then we go ahead, in between all these things, we have batch normalization and also dropout, and also ReLU, right? So we have the first 1D convolution. Then we go to the 60-head transformer with a hidden dimension of 20 that we talked about. And then we have another 1D convolution that takes our 50 channels and brings it to 1. So basically a linear combination of all the channels, which we then pass through a ReLU. And then we put that into a fully connected layer, right, which goes from 340 to 128, then 128 to 2, which we then do a softmax over, which allows us to have a prediction of whether or not this element is a seizure.
So let me take you guys through our training pipeline for this project. So the dataset is composed of raw EEG files. That means that the EEG files are straight from real patients in Temple University Hospital. So the data is not cleaned in any way. So for example, the different EEG files would have a different number of channels, a different combination of those channels, and even the same channel in 2 different EEG files could have a different name. Now add to that the different EEG files are sampled at different rates. And as we mentioned earlier, the amount of seizure data points in the total data set is only 6%. It's very low. So as part of our data pre-processing, we addressed all 3 of these issues. So we found a uniform set of channels that appear in all the EEG files. We resampled all of these files to a uniform sampling rate, and we found a subset of our training set that is normalized, that has roughly a 50-50 amount of non-seizure and seizure data. So now that we pre-processed the data, we used that to train our model. We ran a lot of different kinds of models, but we settled for the one tabs for what Johnny described previously. We would checkpoint the model at all sorts of different places. So after every training epoch, we would checkpoint the model, as well as every time we reached new highs in sensitivity, specificity, and max accuracy. Now, when we want to validate the data or evaluate our model, we would take our trained model with the checkpoint that we want to evaluate. We would run that model on another validation set, and we would take the model outputs, pass them through our post-processing script, which we'll talk about in a bit, and then pass the output of the post-processing script through different evaluation metrics. And we'll talk about that as well just now.
So when the predictions come out of the model portion that Johnny talked about, there is a lot of oscillation between the 2 labels of background and seizure. And we're going to get to the scoring metrics that we used in a minute, but in those scoring metrics, this is very, very bad, and it skews our results in the wrong direction. So in order to correct for this, we used a couple of different filtering methods. So the first filtering method that we tried is voting, where you just, for a particular sample, look before and after, see how many seizures before and after, and then determine whether this particular sample should be converted into a seizure. We also tried a moving average, which is a low-pass filter, and surprisingly, this did not work well. And finally, we tried the Savitsky-Golay filter, which is a filter where you supply a window size and an order for the polynomial, and then you fit polynomials of that particular order over the given window size, and this smooths out the data. So in addition to smoothing out the data, you also have to threshold, which means you have to push the data either to a 0 or a 1. And you can see in these graphs that the top is the ground truth, the middle is the prediction when it comes out of the model, and then the bottom is after smoothing. So the smoothing really, really helps. when evaluating our output, there are many, many ways to do this because we're dealing with a time series where the label of seizure spans over many different times. So two different metrics that we cared about were the OVLP metric and the TASE metric. And the main difference between them is that the OVLP metric doesn't care about how much overlap there is. As long as there's overlap between the reference and the hypothesis, it's counted as a true positive. While the TASE metric looks at exactly how much overlap there is, and it weights the scores based on the overlap. The TASE metric is just a much of the OVLP metric, but the competition that we participated in uses the TASE metric. So we had to keep both in mind while building our model.
So this results page is just to show you guys that we experimented a lot with our models. So the transform model 7 on the leftmost column just describes the tabs model that Johnny described. If you look all the way at the right, you see our sensitivity, specificity, and false alarm rates for these different models. Right in the middle, we have our best results, where we got 30% sensitivity, 89% specificity, and 26.9 false alarms per 24 hours. And this was all using the OVLP method.
Yeah, so our conclusion is that we showed that the deep learning could take place of the signal processing pre-processing stage. We showed that that's possible. We also showed that our results are comparable to their state of the art. And we also showed that the scoring metric has a large influence over the results. So you see, we train with cross-entropy loss, but cross-entropy loss is not penalizing for what TASE penalizes us for, right? Which is how far off you are. In addition, their point metrics in their actual competition weighs the false alarms much higher than it does being correct or sensitivity. So these are things that we had to sort of take into consideration and settle.